Hello and welcome to this lecture series on chemical engineering, thermodynamics of systems. We have been discussing a lattice model of a condensed phase, either a liquid or solid. And in this part of this lecture, we'll be discussing and presenting an introduction to phase change. The material in this lecture is based primarily on the content from Molecular Driving Forces by Dill and Bromberg. So at the end of the last part of the lecture, we sort of gave a summary slide on what have we done so far, and I am essentially repeating that slide here as a sort of prelude, as a sort of a context setting. So what have we done? We created the foundations of thermodynamic analysis, thermodynamic formulation. Then we developed a simple model for an ideal gas and ideal gas mixtures. We then used the thermodynamic formulation to predict measurable or obtain measurable properties of the ideal gas phase, as well as those of ideal gas mixtures. Then in the previous part of this lecture, we developed a simple model for a condensed phase, whether a liquid or a solid, of a pure substance. Then we turned our attention to the coexistence of both the condensed and the vaporized phase, used a criterion for thermodynamic equilibrium between the two phases by equating the chemical potentials of the pure substance in both phases. And then by eliminating the chemical potential, we obtained the relationship between the vapor pressure and temperature. Of course, then this gives rise to, PT relationship, so which can be then plotted as a coexistence curve, which is what we're going to take up and try and discuss in this part of the lecture. So we can then, in principle, construct a PT diagram for a pure substance based on the expression that we derived for relating the pressure of a vaporized phase with the temperature as a function of temperature. So one of the important consequences of this simple model of liquid that we developed, which is in equilibrium with its ideal gas, of course, this is there that the gas is considered an ideal gas, is that the vapor pressure exhibits an exponential relationship with temperature. So typical PT coexistence curves are captured in the following phase diagram. So the high pressure, low temperature region corresponds to solid, and the low pressure, high temperature region corresponds to gas, and then intermediate phases are liquid phases. There is this particular point called the critical point, which we will not discuss in this particular lecture or in any of the subsequent lectures for a series of lectures. So observe that the PT curves between a solid and a liquid and a solid and a gas appear almost linear. And this is basically the consequence that the epsilon AA is very large. And therefore you are looking at a small value of exponential change, and therefore that is approximately a linear behavior. And also keep in mind that for a solid liquid equilibrium, a bond need not be fully broken, as with gases. Of course, a fully broken state in the sense that you are not ascribing complete translational degrees of freedom to a molecule that has gone from a solid to a liquid phase, and hence there is additionally weaker dependence. So now, before we take up this PT coexistence curves, this is an appropriate time to sort of revisit what are the ideas of degrees of freedom, and we'll obtain an expression for the so-called Gibbs phase rule. We'll connect this to the state postulate, which we started out with. From the PT diagram, we observe that for a pure substance, we only need to define either a temperature or a pressure to determine the state of the system when the two phases coexist. At the coexistence, along the coexistence curves, which basically is a, this is a two-dimensional system, and therefore there is one variable temperature, the other variable is pressure, and so if one is defined, the curve will give the other variable. Further, there is a unique point called the triple point, which is the junction point of the so-called Y-shaped PT curve, where all the three states, solid, liquid, and vapor or gas, coexist. On the other hand, if you were to be anywhere outside of the coexistence curves and the triple point, one needs to specify both pressure and temperature to determine the state of the system in a single phase region. This much we can gather from the picture, the PT phase diagram itself. To understand this further, we now revisit the state postulate, which defines, of course, the number of independent variables needed to uniquely define the state of the system. Right. So consider the running example that we've been looking at as a glass of water. If we were to consider the vaporization of water through the water-air interface, this boundary is diathermal, moving, and permeable. So typically what we do is we assume that there is both thermal and mechanical equilibrium already, and then we say that hypothetically at time t equal to 0, when I placed my glass of water, that the boundary became permeable and there is vaporization continuously happening at the fixed temperature pressure. So now if we fix the total number of moles of the substance across phases, so the total amount of water that we took is defined, all right, so the n is fixed, so that is 1 degree of freedom that we chose already. Specifying the temperature and pressure defines the thermal and mechanical equilibria that exist between the water and its vapor. What it means, given that there is a thermal and mechanical equilibrium between water and air, in the running example of glass of water, if we insist that there has to be two phases which exchange species, so in other words, we assume air is insoluble in water, so we assume that water is present both in the liquid phase and the vapor phase or the gas phase, and the two phases, the water in both phases are in equilibrium, then there are only two independent variables, namely temperature and pressure. This is because the third variable, which would be chemical potential, it's a function of temperature pressure as per Gibbs-Duhem equation. So now we try and define the degree of freedom, which is the number of independent variables we need to uniquely specify the state of system, from the general definition. In a general system, how do you define degree of freedom? Degree of freedom is defined as D is V minus E. V is the number of variables, E is the number of equations that constrain or relate these variables. So we sort of postulated that there are three variables that uniquely specify the macroscopic state of the system. TPN, for example, if you were to consider a free interface, right, which is given by the number of work modes plus 1 for the heat, right? We just postulated this. So how many equations are there? How many equations relate these three variables? If there is a single isolated phase, meaning either only a liquid or only a gas or only a solid. So if you take water, water is present as ice or liquid water or steam, pure steam. And in the absence of any internal driving forces, which means, that means there is an internal driving force driving change of state of internal state of a system. So you would then look at two subsystems within that particular phase whose equilibrium has to be studied, like we considered when we derived criteria for thermodynamic equilibrium. All those internal driving forces are not there, then there are no equations relating temperature, pressure, and number of moles. All right, and therefore the number of variables equal to 3, number of equations is 0, degree of freedom is 3. These three independent variables are indeed TPN. Now on the other hand, when two phases coexist, then one can define the equilibrium between those two phases by requiring that dg has to be 0, which is basically this expression. So this expression means that there is one equation relating the three variables, and therefore the degree of freedom is 2. okay, but you fixed n, and therefore if you specify either temperature or pressure, so for a fixed n, specifying temperature or pressure will specify this two-phase coexistence region. Now when all three phases coexist, such as in the case of a triple point, so one can write two such unique relationships, dg equal to 0, between basically change in the Gibbs free energy of one of the phases, for example a liquid, because of interaction with the solid or because of interaction with the vapor. So there can be two such expressions that can be written. The third one will automatically be satisfied. So if you write one for liquid, one for vapor, one for solid, only two of them will be unique relations, and therefore you'll have two equations, three variables, degree of freedom is 1, and that 1 is basically the number of moles that you fix, and therefore for each material there is a unique triple point that specifies the three-phase coexistence. Of course, why do you need this 1 degree of freedom? It is, of course, when you are saying that you are specifying the energy of the system, this is an extensive quantity, and somewhere you have to specify the extensivity. So that's specified here in terms of number of molecules or number of moles or mass, or whichever way this n is measured. So what do we understand? We understand now that therefore the state postulate is a specific case of general definition of the degrees of freedom in a system. So we started with that hypothesis or some sort of a postulate. We said that, hey, this is what we take it to be, and it turns out that it is actually a specific situation for a more general degree of freedom. The above arguments, of course, can be extended to multi-component systems, and this will result in the familiar Gibbs space rule, which you may have studied in your school, where the degree of freedom is given by c minus p plus 2, where c is the number of components and p is the number of phases. So when we discuss multi-component mixtures, now we are looking at phase equilibria involving pure substances. When we move on to multi-component mixtures again, at that time we will derive this phase rule. Now let us come back, after this sort of a detour, come back to the vapor liquid equilibrium between two phases containing a pure substance. Now we developed an expression for the vapor pressure of that the gas, the vapor phase, as a function of temperature. But is this did this contain measurable quantities or not measurable quantities? If you look at it, we try now to create an expression for vapor pressure which contains measurable quantities. So that leads to the so-called CLAYPERON equation. So the vapor pressure shows, of an ideal gas, shows an exponential dependence on the temperature of the two-phase system. Even for a non-ideal gas, the dependence, the functional form will be the same. So this is the expression, but as I just mentioned, this is not measurable. Since epsilon A is not easy to measure, especially as a function of temperature, for most systems, an alternate relationship is explored. We again start with mu g equal to mu L. Now let us consider the coexistence curve and consider 2 points along the coexistence curve, 1 and 2. At both points, okay, if you look at point 1 and point 2, at both points we, this is the coexistence curve. We of course have to have mu g equal to mu L. So mu L at point 1, which corresponds to T1 and P1, should be the same as mu g at T1 and P1. Similarly, mu L at T2, P2 would be equal to mu g at T2, P2. So these are the corresponding expressions at both points, which are the criteria for thermodynamic equilibrium. Now, if these 2 points are infinitesimally apart, we just chose them any arbitrary 2 points along the coexistence curve. So if they are infinitesimally apart, then we can write mu L at 2 is mu L at 1 plus some d mu L, which would be a function of temperature pressure, where the Tp would range between T1 P1 and T2 P2, right? Similarly, mu G at 2 would be equal to mu G at 1 plus some d mu G, which is a function of temperature and pressure. But the criteria for chemical equilibrium require that these two are equal as well as these two are equal. Therefore, this differential change in chemical potential of a liquid must be equal to the differential change in the chemical potential in the gas phase. So this means d mu L is d mu G is d mu of Tp. So keep in mind that the total n is fixed along the coexistence curve. Keep in mind we discussed this degrees of freedom and all that. The total n is fixed, right? So this infinitesimal change in chemical potential is then given by, since it is a function of temperature and pressure, one can write this as dou mu dou T at P dt plus dou mu dou P at T dP. Of course, I have to put comma n as constants. N is fixed in both these differentials. Now, of course, we have Tp, so we turn to our trusted friend Maxwell relations involving n. Therefore, that's when you will get the chemical potentials. So dou mu dou T at Pn is dou S dou n with negative sign at Tp, which is basically, of course, molar entropy at constant temperature pressure, which of course is any point along the coexistence curve. So the whole thing is valid only along the coexistence curve. That's what we are saying. So dou mu dou P at Tn is dou V dou n at Tp, which is molar volume, again at constant temperature pressure. So this minus S and plus V are only at those points along the Pt curve. So therefore we have d mu at Tp is minus S dt plus V dP. All right. The criterion for thermodynamic equilibrium, phase equilibrium, gives this d mu at G is the same as d mu at L. So minus Sg, which the superscript denoting the vapor phase or the gas phase, and the L denoting the liquid phase. So we just equate these two relations. And then we can, of course, collect the terms involving temperature and pressure. We can then get the slope of the Pt curve because we can get dP dt. So dP dt is Sg minus Sl divided by Vg minus Vl. This is simply delta S by delta V. So along the curve, as you go along, what is the change in entropy with respect to change in volume? Of course, molar entropy, molar volume, fix the total number of moles to be constant. So that gives us the slope. So basically, because there is an increase in the molar volume, for example, by vaporization, what is the corresponding increase in the multiplicity? That essentially tells us, how much is the vapor pressure going to increase as a function of temperature, which is exactly the argument that we posed. So if there is more, entropy that is to be gained, then the molecules will tend to go into the vapor phase, and therefore the more of the molecules will go into the vapor phase, which will then exert higher pressure back on the liquid. So this is exactly what is captured here. In other words, the slope of the Pt coexistence curve is understood by the ratio of how much increase in molar entropy, right, per unit volume, right? So takes place due to the vaporization of a liquid. Okay, so how much there is increase in molar entropy due to increase in molar volume. So how do we estimate this delta S and delta V? This is the question now. So for this dP dt to become measurable, we need to be able to estimate the delta S and delta V. Fortunately, we have a simple enough way to estimate delta S. Partial molar Gibbs free energy is basically mu. Once again, we sort of fix this, use this G by N as mu, molar Gibbs free energy. In this case, we don't even need to consider partial properties. Molar Gibbs free energy satisfies the condition delta mu is delta H minus T delta S. This should be 0, right? So the liquid phase and vapor phase, the change in chemical potential has to be 0. Therefore, delta S is simply delta H by T. So we end up writing this expression for dp dt. If we can capture what is the change in volume due to vaporization, this is basically what is called as latent heat of vaporization. Or this is, of course, this could be valid for any phase change. So this delta V could be due to melting, and this would be latent heat of melting, and this delta V could be if you were going the opposite way, freezing, and this would be the latent heat of freezing, and this could be condensation, sublimation, deposition, whichever it is. So this expression is pretty powerful expression. So this is delta H is the change in enthalpy due to vaporization. In this case, we are looking at vapor liquid equilibrium, which is latent heat of vaporization. This is measurable. How much energy did I supply to vaporize 1 kilogram of or 1 mole of substance, right? So if we can determine the change in molar volume due to vaporization, and if we knew one point along the PT curve, because to integrate this you need an integration constant at the end of the day, then for example, for water at 1 atmosphere, the boiling point is 100 degrees Celsius, right? So this is pure water. Of course, there is no air or anything involved, right? So 1 atmosphere, 100 degrees Celsius, right? So 373.15 Kelvin. So then all the liquid vapor coexistence states of the system may be determined if only we could calculate the change in molar volume due to vaporization. Now, if we can then simplify, if we assume the vapor phase to be ideal, then PV is RT, keeping in mind, then delta V is simply Vg minus VL. Then we further make the simplification that VL is much, much smaller than the gas phase. And so we approximate this delta V to be Vg. Basically, there is more than 100 times increase in volume typically when a liquid vaporizes to gas phase. So this approximation is not terrible at all. Now this is then replaced by RT by P, and therefore Clapeyron equation becomes dp by dt is lambda vaporization times P by RT square. In other words, if I take this P to the other side and then I recognize this is d of ln P over dt is lambda vaporization, which is latent heat of vaporization, by RT square. This equation is called the Clausius-Clapeyron equation in the differential form. Once upon integrating this equation, then we get ln of P2 by P1 is minus latent heat of vaporization by R into 1 over T2 minus 1 over T1, because when you integrate 1 by T square, integral dt by T square gives you minus 1 over T, and so the limits would be 1 over T2 minus 1 over T1, of course, with a minus sign here. Now notice that pressure is an exponential function of temperature, as we observed earlier in our expression, but this contains all completely measurable quantities, and therefore this equation is of great value. So so essentially this sort of tells us something to the form that log P vaporization is some A by T, all right, plus some constant if there is a reference state that you want to consider. And such an expression is what is typically used to sort of fit vapor pressure and temperature data, and that empirical expression is often that is used is called Antoine's equation. So A minus B by T plus C or something like that is what is used, right? So the A probably comes from here, minus B by T plus C comes from this term, so to speak. So to summarize, we in the previous part of this lecture, in this lecture, we have developed a simple lattice model for a pure condensed phase, whether it is liquid or solid. We have obtained an expression of chemical potential of the phase in terms of the bond energy of the molecules or particles in the condensed phase. This is typically secondary bonds. Using the criterion for phase equilibrium with an ideal gas, we obtained the relationship between vapor pressure and temperature in terms of this bond energy. We then constructed PT coexistence curves for a pure substance. We then revisited state postulate, degrees of freedom, and constructed the Gibbs phase rule for a pure substance. Didn't extend it to multi-component systems, mixtures. But for a single component system, we did obtain the Gibbs phase rule. Then we constructed the general thermodynamic framework for obtaining slope of the PT coexistence curve and obtained the CLAYPERON equation. Now for the ideal gas phase, this was reduced to Clausius-Clapeyron equation, which showed the same exponential relationship that was obtained by the simple lattice model for a lattice liquid and the ideal gas. As we come to the end of this lecture, as always, please feel free to contact me if there are any questions. Thank you very much for listening to this lecture. I hope you have a wonderful day. Thank you.